I'm going to go ahead and introduce Peter Garba and Vikas Gupta, who are going to talk about de-obfuscating WebAssembly using LLVM. I think one of the interesting things about a lot of the talks you're seeing here is that people are connecting tools in different ways. They're working with, obviously compilers at all different levels. And I think that the main goal here is to give people tools to think about these problems and to solve new things on their own. And so by seeing what people are doing and how they're applying things like using LLVM to do optimizations or de-optimizations, you guys should be empowered to solve new problems even as they come up. But also, just practically speaking, if you happen to be working on some of these problems, you can get some things that will help you right now today. So please welcome to the stage Vikas and Peter.
Okay, thank you, Jordan. So first and foremost, thank you for everyone to coming for our talk. And thanks to the organizers. It's been fascinating so far. It's a great conference. Let's get started. So our talk is about de-obfuscating WebAssembly using LLVM. And we have a trade offer for you. So you give us a Wasm-obfuscated binary, and we give you a de-obfuscated one. But before that, a quick introduction about us. So myself, Vikas. I work at Thales DIS as a pen tester. Previously, I was with Google for Android security. And I try to contribute to the mobile application security using MSTG, like contributing to MSTG or Wasm MSTG guide.
Peter? My name is Peter Garba. Hello, everyone. I'm a product owner right now, somehow ended up in this position. Before, I had several security positions within Thales, like be responsible for their internal obfuscators. So right now, I shifted basically my reverse engineering to the night shift. Yeah, why WebAssembly? Within Thales, we deliver software or components to different platforms like mobile or web or even Windows. And our customers have the interest to move basically more of the code into the web. So we look into different technologies, and we identified WebAssembly as one of the solutions because we could reuse our internal obfuscator as it works on LLVM IR. And basically, all of the tools are based on LLVM IR for WebAssembly. And of course, we wanted to know if it's secure. I mean, can we protect our components within Thales? And basically, the best way to do this, we thought, OK, let's try to attack it. We obfuscate a sample and try to attack it and see the results, right?
And yeah, that's where my role comes in. So yeah, I collaborated with Peter, try to break things. Let's see how far we go, how secure it is for our products. And that's how all of this thing started. OK, so we have a few problem statements now once we started collaborating. So first and foremost, as Peter said, is it secure enough for our use cases? And then in terms of tooling, how can we obfuscate the Wasm binaries? How we can de-obfuscate them? And among all of this, one of the important questions came up, how do we lift Wasm to LLVM IR? So we'll take you through the journey, how things were.
So what are our achievements? We're going to demonstrate existing tooling, what's out there for obfuscation and de-obfuscation. We're going to introduce a tool that we're working on. It's called Squanchy. It will help us to drive the de-obfuscation process. So we go into details, how it works. And we will present you our basically pipeline, how we try to automatically de-obfuscate WebAssembly samples.
OK, so quickly, some quick introduction about WebAssembly. So it has been around for a while. It was introduced in 2015. It's a compilation target, so you can take some high-level language, compile it to the WebAssembly. It works on a stack-based virtual machine, so you can relate it to like JVM. And so you take like C++, Rust code, compile to WebAssembly, then you have various runtimes like in the browsers or Node.js, and you can run your WebAssembly binaries. This is how a sample code looks like. Luckily, we don't need to look at such code in our presentation, so it's just a representation. So this is like a text format representation of WebAssembly binary for an add function. This is how it looks like. Each WebAssembly binary is kind of called a module. So module is like the basic unit. And each module has some sections. So sections has all the information that we are interested in. So for example, like the imported function, exported function, all these tables are there in these sections. There are some sections which we're more interested in this talk. For example, the tables, the globals, the function tables. And we'll see later on like how we are using this information. Now, there are some interesting design decisions with WebAssembly. So everything, as I said, like is kind of tables. So you kind of use indices to access this information. For example, you want to get access or you want to run some function. So you specify the index on which that function is. The function gets executed. Similarly, for the memory as well, like there is a long linear array. And yeah, you specify the index in the array which you want to access at. You don't have access to the, or the code doesn't have the access to the real addresses, and which kind of adds to the security. Like you cannot mess up things now because you don't have access to the real addresses. In similar things, so even for control flow, you don't have arbitrary jumps. So everything needs to be well-defined, concrete. And so in other words, no go-to, no funny things. And over here, you can see that these are some of the instructions which are used to define the control flow.
Yeah, maybe one thing to add here. We don't have any indirect branches, which is kind of cool because when we're going to live from x86 or ARM, the obfuscator might indirect those basic blocks, right, the jumps. And we need to, we cover them during exploration of the CFG. With WebAssembly, we don't have this problem. We can directly recover the whole CFG while we're going to lift the code into IR or C.
Yeah, we have an example for this one as well. Yeah, a quick idea about the tooling. So tooling is developing quite fast, I would say. And in terms of the command line tools, the top two are the ones which covers most of the use cases. We are quite interested in Wasm-mutate. You will see we heavily use it. And then we use Wasm-mutate as well. And in terms of Ghidra and IDA, okay, so Ghidra, you can use it with a plugin. So out of the box doesn't work. You use a plugin, and you can get some nice decompilation. And it's pretty robust. Like in our use cases, it worked. With IDA and JEP Pro, the licenses we have, we tried. It's a hit and a miss. For some binaries, it works. Some binaries, it doesn't. So we predominantly stick with Ghidra for this use case. Okay, so now let's talk about obfuscation. So I think all of us over here understand the need of obfuscation and why it's there. Just a quick reminder that when we are doing obfuscation, we are trying to make things harder to read, to reverse engineer, but the original logic, the original semantics of the binary, they're still there. Use cases, of course, malware authors love them. But other than that, on the other side, yeah, you want to protect your IPs, which is, I would say, the case with Thales, that we want to protect our IP, so we obfuscate a lot of code we have. And yeah, for digital rights management as well. And there are more use cases as well. In case of WebAssembly, so we can apply obfuscation at different levels. So let's say if we are starting with C source, you can use tools like Tigris, which is open source, apply the obfuscation right over there. Or you can apply the obfuscation at the LLVM IR level. So for example, OLLVM tool is there. We will be looking more into such kind of tools. Or if you have WebAssembly, you can apply Wasm-mutate as well. Again, we will be looking into this use case as well later on in our work. So for now, let's start with the LLVM example. So LLVM pipeline is divided into three parts: front end, middle end, back end. And these obfuscators that we are talking about work at the middle end. So there's these obfuscation passes which obfuscate the code. For our work, we took three open source examples which are there, or the projects which are there: OLLVM, Hikari, and Polaris. And yeah, the good thing about these tools is that they're language agnostic. So not just WebAssembly, you can apply for anything else as well. Yeah, quick summary about the features these tools offer. So OLLVM, I would say like the OG one, the real, like started this whole revolution in a way. Hikari and Polaris is like a gradual evolution. So for example, with Hikari, you have few more passes like string encryption, indirect branching, which just we talked about. With Polaris, you get like obfuscation using linear MBAs. So things are evolving. How to apply? So it's quite easy, actually. So it's just a two-step process. So you use one of the obfuscators and generate the LLVM IR, which is the obfuscated IR. And in the second step, you can use EMCC, which is like one of the compilers based on Clang. Or you can use Clang itself with the, by telling it to generate Wasm. So it's quite easy. Some examples. So I know some of the code might not be visible right at the back, but what I want you to focus is on, like, there are 4 expressions in this code. And you can see how they evolve, like they become complex when we try to obfuscate them. So on the left-hand side is the original code with 4 expressions, and on the right-hand side is like a very basic example where we are applying OLLVM instruction of substitution, and you can start seeing that these expressions are becoming bigger and complex. Similarly, if we do flattening and block splitting, so the control flow graph kind of blows up, it becomes bigger and bigger, and things can get, you apply different passes, things start to look more complex. So this is the case with bogus control flow using Hikari obfuscator, opaque predicates are inserted into the code. There are a lot of branching and stuff, so things are becoming complex. Touching back on the point of indirect branching, so as we mentioned earlier, Wasm doesn't support it, and you can see in the real example over here. So on the extreme right, we have the case if we apply indirect branching for x86 program, you see that the basic blocks are kind of disjoint. There are no clear joining or the path between the blocks. But in the middle, you have for the WebAssembly, and everything is quite connected. Like there is no disjoint, no go-tos, no arbitrary jumps over here. So what you can do is you can apply these obfuscation like multiple times, like 2 passes, 3 passes, multiple of them, and things become really complex. So the simple code that I showed you, like 5 or 10 lines of code, in one cases we saw that the size ballooned up to 12 megabytes. So that small code becoming a 12 megabyte binary. Decompilation looks like 2,000 plus lines of code. I have some examples over here, like after a certain size, like Ghidra stopped working, it just gave up. On the extreme right is the case where, it's kind of unreadable. Like they are like nested while loops over there. And of course, in the middle, we have the example where, the control graph is a mess. Like you don't want to see such things. Obfuscation.
So let's take a look how we de-obfuscated binary in the past, like 10, 15 years ago. We were lucky. The tools that existed to obfuscate were basically working on assembly level directly. So what they did, they created those replacements or patterns they were using directly to replace the opcodes by a specific pattern. They also had like obfuscation patterns, constant unfolding, so they tried to hide those constants, and they injected junk code to hinder tools like either to disassemble the function properly or just to fool the attacker, right? So back then, our job was easy. We tried to find those patterns, right? Like here you can see one pattern around 2010 that was welcome in PC games. And this pattern, after we took some time to identify what they were doing, we could simply identify, oh, this is a jump. So this is all it does, right? So we were coding those pattern downs in our tools. Basically, over time, we found new patterns when there were new versions of games. And and then we just replaced pattern by pattern until the code is folding, and we reconstructed the original code. Unfortunately, this has changed. So modern obfuscation looks different, right? We don't see those patterns anymore. What we see is those huge graphs. And this is because they have better technologies now. They build the tools now on IR level. They, as Vikas showed before, they use LLVM IR. They directly have the full control over the control flow graph. They have the control over each instruction, so they can do much better work. But this is hard for us, at least it was in the past, because we didn't have the right tools. So for a long time, they were like ahead of us. But things have changed. So with modern de-obfuscation, now we have those binary lifters. We have like the decompilation IDA. We have binary ninja with several IR levels. So things become easier for us. So like in this example, before it was obfuscated code like this, full graph, you don't understand anything. But after the obfuscation, you will figure out, oh, it's just one easy function that just returns a sum over some parameters, right? So in 2019, Matteo Favaro and I released a paper about binary de-obfuscation based on LLVM. So what we researched back then is, or what we noticed is that compiler optimization do a pretty good job at removing those kind of patterns. So when we lifted this code, back then we used trade-off bits remil, or we still use it, we could get the code into a shape on LLVM IR where the optimization starts working, and they were folding this code very nicely. And this approach still works today, and it weakens certain obfuscations, and in best case, even removes the obfuscation completely, which is great to see. So you can use compiler optimization to remove the obfuscation. Yeah, and this is basically how the tool works back then. I mean, we have as input, we take one of the binaries, ELF or PE, then we're using remil from trade-off bits to lift the code into LLVM IR, but this code is not really usable. If you're going to optimize it, it will not fold. So we have specific optimization passes that we implement on our own, or just use the LLVM pipeline. We try to detect the upper predicates, we try to handle MBAs and so on, and once we are done, we try to get the code into a nice shape. Here we call it brightening, so we want to make it readable for humans. I mean, you want to reverse engineer the code afterwards, you want to understand what it does, right? So we try to do this brightening step at the end, and once we are done, there was one cool thing about LLVM, you can always compile down to a binary. So either you started with a PE, you can create a macro at the end, you started with x86, you can create ARM64 at the end. It doesn't matter, the LLVM just will take care of it for you.
Okay, so with this idea that compiler optimizations can work, so we started looking at, okay, how we can have some tools without writing much of our own, achieve such goals. So we started with Binaryen, and it's a compiler tool chain which is specializing for WebAssembly. And the good thing is that you give the input of a Wasm binary, and the output is Wasm binary, and in between it performs some optimizations. We took a simple example, like OLLVM instruction substitution, feed into this, and yeah, let's see if the de-obfuscation works or not. Unluckily, it didn't work. So yeah, we were like this, thinking about like what to do next, because this thing doesn't work anymore. So now we have the question that, yeah, we need to do something with the LLVM IR, which was proposed with Saturn, the original paper by Peter, and let's get started. So
yeah, why LLVM? LLVM is the target-independent optimizer and code generator. The advantages are it has world-class optimization techniques. The best companies in the world have the best engineers working on this tool. They're writing optimization passes. You have people in academia that try to prove that those optimizations work as they should, yeah? So you don't have miscompilations. And we get it for free. It's open source, right? And it's used basically everywhere. It's there to compile your kernel for your Android phone. It's used in macOS for the kernel, for the operating system. So everything depends on LLVM these days, more or less. I mean, we still have GCC, but who knows? Yeah, then it has accessible APIs. The APIs are written to be used by engineers, and they are really good defined. I mean, if you want to modify a control flow graph, if you want to change instructions, you're free to do what you want. There is basically everything that you need. World-class analysis passes, LES analysis. It's awesome if you get it into the right shape, right? And it's fast. It's meant to compile the biggest code bases, like the one from Chrome, in a good amount of time and deliver you fast executing code. Yeah, so it's awesome.
But before we get into this, there were some challenges which we should be mindful. So when you're lifting from one representation to other, so we need to take care about the correctness, whether we are expressing in the same way or not. And then, yeah, whether you have the correct runtime information, which we will see in this case that it was important for us. So yeah, there are some challenges. We need to be mindful. And
yeah, this is just a quick example. So how would you lift WebAssembly into C? So here on the left, we see WebAssembly assembly code with some opcodes. In the middle, we have the specification. The good thing about it is that we don't have any side effects. If you would lift x86 opcodes or ARM64, you would need to deal with the E-flags or all of kind of effects that this instruction might have. In WebAssembly, we don't have this. If there is an addition, we just add it as an addition. And on the right, you just see some implementation of one of the lifters. They really just emit a plus for an addition, nothing else. So it's pretty simple. Yeah, the good news is everything is already implemented. So we don't need to implement the lifter on our own. There are tools that take the code on the left, the Wasm code, and lift it to a kind of pseudo C code that you can compile. It's not perfect. It's not fully readable, but it's semantically correct. So if you're going to compile and execute it, it will behave the same as the original WebAssembly code, which is a benefit.
OK, so again, we started looking around for the tools which are already doing this lifting. So we came across this runtime called WebAssembly micro runtime. And this runtime has a compiler, which do a AOT compilation for these Wasm files. And it generates LLVM IR. So, and there is an option that you can emit the LLVM IR. So we used this tool and did some testing. It was OK. But soon, once we get into the complex examples, we see the shortcomings of this approach. So first and foremost is that we lose all the symbol information. So if you see in the image that the functions are renamed to like AOT function 0, 1, and so on. So information is lost. And the most important thing for us was that all the meta information, like about the tables that we showed you earlier, that information is not available in the IR. So maybe WAMR is using in some other ways, in some other representation. But in the IR format, this information was lost. So this kind of hampers us when we start getting into the de-obfuscation passes using LLVM and all. So yeah, we were back to the drawing board, mostly plus nights. And again, so we still have this block kind of question mark, like what to do.
Yeah, so we looked at basically all the lifters out there. As Vikas mentions, Binaryen has this property IR, the Binaryen IR. We don't want to write our own optimization passes. We want to rely what's there. The code is not falling, surprisingly. At this point, we didn't understand why, but we didn't care. So we moved on. WAMR SC, yeah, it's lived into LLVM IR. One thing to mention, it has an instance parameter. Might be interesting, but we don't talk for this for now. The code was falling partially, but when we used more bigger samples that used like tables and so on, it didn't fold anymore. And we started to understand, OK, there is missing something. We need to look into this. And then I came across Wasm-mutate. So unfortunately, it's lifting into JavaScript. But when we looked at the code, JavaScript looked more like C pseudocode. So after you added a semicolon and some go-tos, you could easily compile it. And it was working fine in C. So I thought, OK, the code looks really clean, much cleaner than the others. And I spent like about a week to try to make it work. And during this work, I implemented support for the tables, external references, basically everything what's there, what Vikas mentioned in the beginning. And after some time, I discovered, oh, I'm basically re-implementing Wasm-to-C because everything is already implemented in Wasm-to-C. So then we switched after one week to Wasm-to-C. But the good thing is the learning curve was great because I started to understand deeply how it works, how everything is connected. So it really helped us. So Wasm-to-C, yeah, it's a good candidate for us. So here is the lifting idea. We take WebAssembly code. We use Wasm-to-C to lift it into C pseudocode, I would say. Then we compile with Clang. Here we don't apply the optimizations, so we use O0 to emit LLVM IR. This is important these days because in LLVM, they introduced the concept of opaque pointers. So after you optimize, you will use type information. And we need type information at the beginning. You will see later why. So we just compile with O0, so the type information are there. Then once we are on the IR level, we have the optimization options that we could use, the runtime and helpers. And then we can emit LLVM IR again and compile it into a binary, or we just compile it into WebAssembly. And we can use tools again to decompile, and we don't need to write a decompiler. We can just rely on what's there. And yeah, that's the idea. So what's Wasm-to-C? Yeah, it's a great tool to lift Wasm-to-C. The good thing about it has a well-defined Wasm runtime. So it means once you lift your code into this pseudo-C, you can recompile it. You can recompile it. You just need to implement the driver. It's not difficult. And then you can just execute the code and it behaves the same. As long as it doesn't access some specific features from the browser, it should work, right? So it was a good start. It also has helpers for loads and stores. So it's not directly emitting, writes the data into the stack slots. We have helpers for that. You can override those helpers, which is quite useful. We don't use it, but maybe in future we might. And it doesn't modify the control flow graph. So basically, when you look in Ghidra at the WebAssembly, and after you compile the Wasm-to-C code without optimization, you see the same control flow graph. And this is a big benefit, because we want to keep the control flow graph, at least in the beginning, in its original state. So here's a motivating example. This is just an add function. There is a loop that calculates the constants. Normally, a compiler would easily optimize this into this constant, but we compile it with O0 to make it a little bit more difficult. Then we see an MBA-based opaque predicate. So this is this long expression on the left minus another expression. If it's equal 0, it will sum 1911. If it's unequal to 0, it will sum another constant. So which one is chosen? you can guess. And afterwards, it sums everything together and returns it. So if we apply our idea how to de-obfuscate, we always want to reach the best optimized code at the end. So this is the idea. OK, here's a simple example. Here, make it a little bit more simple. So we directly take the optimized version, lift it with Wasm-mutate into the C code, and now we can see, oh, we apply optimizations now. The code is folding nicely. The LLVM IR has now removed most of the variables and the sex log. We end up with perfect decompiled functions once we open it in either Pro or in Binary Ninja or Ghidra. Yeah, doesn't matter.
OK, so some information about Wasm-mutate. So if you use Wasm-mutate, you will see that every function call get this W2C instance. So now this instance thing is quite important. This instance is keeping the information about the runtime, basically. So for example, there is this memory structure, which we are showing in the code. This information is there. Information about the function reference table, about the globals. So basically, the information which wasn't there in the WAMR lifted LLVM IR, all that information that we wanted is there in this one.
Yeah. OK, so when you want to execute lifted Wasm-mutate code, you need to instantiate the Wasm-mutate struct. And this instantiation is dynamically generated. So if you don't use specific features, it will just leave some of the initialization functions. But in this case, it will instantiate the import, the global, table, memory, LM, and data. Yeah, so it's quite useful. It will be automatically generated, and we can just use it for our purposes later on. So now let's extend our de-obfuscation idea. So we have the Wasm-mutate on the left. It lifts it into LLVM IR, kind of. And now in the middle, we have our tool Squanchy. This is the tool that will drive the obfuscation for us. This is where we implement the whole de-obfuscation pipeline. We can attach third-party tools to it. Let's say we want to solve some MBAs, so we can use Simba. We would like to do some heavier things. We can also apply Super. And once we are done, we emit the binary, and then we use LLVM again to target the architecture we would like to and continue with the reverse engineering process. So what is Squanchy? So Squanchy is a tool to automate several de-obfuscation steps. It models and injects the runtime that will help us to fold the code. It inlines accordingly. So one of the things we do, we're going to inline the dependencies into the function. It optimizes the function and module. So here we rely on a customized optimization pipeline to preserve the control flow graph in the beginning. But later on, we will do harder optimizations that also handle the control flow graph. It tries to remove the Wasm-mutate runtime from the module, so you get a clean output. And it expects the function as dependencies in a new clean model, so you can easily further process it. You don't need this loaded code. It's not there. And it's open source. So after the conference, we make it available. So if you would like to play around, you can use it. So what is the idea? I move here. I think it's easier. So on the left, we have our lifted function with Wasm-mutate, with the lifted Wasm code. It has this Wasm-mutate argument, the first one. And then we have the Wasm-mutate runtime that is also emitted into the module that is generated by Wasm-mutate. Here we see the init imports, globals, and so on. And we have the Squanchy and Wasm-mutate helpers. Helpers means we need to somehow allocate memory. Yeah, basically, we lower it down to a C locker. We implement it accordingly, because mentioned it's access to those index. So we need to take care of this. We need to emulate this behavior. We allocate the function refs. So basically, what the whole idea is, as you would dump running application from its memory at its original entry point. So this is what we try to achieve, right? But we don't want to execute any code at this stage. All we want to do is rely on optimizations to do it for us. So the first thing that we do is going to allocate a local Wasm-mutate instance. It will be at the beginning of the functions. And then we're going to replace all the users in the code from the first function argument to this locally allocated Wasm-mutate struct. Then we're going to create a call. This call takes the local Wasm-mutate as an argument, and we call the Wasm-mutate runtime initializer. Yeah? Because remember, when we wanted to execute code, this is what we need to do before. But now we're going to do it locally. And the reason is because as long as it stays global, LLVM will not fold it. The optimization will not work. But if we move it locally, then the optimization starts working because there is no external references to it. Then we're going to mark all the dependencies of those functions with the attribute always inline. Once we do that, we can use the LLVM inliner to accordingly inline the function one after another. We do it recursively, so if those functions have any dependencies that are also marked with always inline, we go and also to inline them into this function. So basically, we end up with a huge initialization block and the obfuscation block, which references the local instance.
OK, so this was actually one interesting thing I learned while working on this project is that, like any software engineering project, you do trade-offs, right? So in LLVM, there are trade-offs that how can you make the code compile faster, but fairly optimized as well? Or the other way around, if you try to optimize it too much, it may run too longer as well. So these are the numbers or the thresholds we are talking about. There are these numbers which you can kind of change and ensure the trade-offs. So in case of de-obfuscation, honestly, we don't care about the time sometimes. We want the simplest code. And we can change these thresholds. So over here, we have examples for two thresholds. One is the death store elimination, and other is loop unrolling. And we maximize them. So we try to get like maximum optimizations which are possible with LLVM, and we don't care about the time.
Yeah, maybe one thing to add. You can see it like that. So sometimes you have a store at the beginning and a load at the end. And because of the thresholds, the alias analysis does not know there is a load at the end. And it's very careful, right? So it will not alias in some cases. But if we increase the numbers, because as Vikas showed with, sometimes we have code with 12 megabytes for one functions, yeah, we need to increase it as high as possible. Then it will know about the load. The alias analysis will start working and can do a better work. So the passes based on this can do better optimizations. Oh yeah, so while we were preparing for this talk, we presented this to the board. And there was a question, why do we need to preserve the control flow graph? Yeah, because this is crucial, at least at the beginning. And this is because obfuscation pipelines are written by humans. It's not like you randomly just choose the obfuscations on your code. I mean, you could do this. But as a product owner, my customers will complain, right? The binary size would be too big. The performance would be too bad. Maybe the security would be high, right? But they don't care. I mean, they can sell it. So I have to make a trade-off. I have to balance the obfuscations to get like a balance between obfuscation size, performance, and security. And then they would take it. And if you think about malware authors, they have the same problem, right? I mean, if the binary is too big, then it might take too long to load the payload on the devices. If the code is too slow, maybe your revenue might be not high enough if you mine Bitcoins, right? So basically, they do the same. And one way to doing this is creating these obfuscation pipelines. So the first thing that you always want to do is take care of the control flow, so you can apply control flow threatening. Then you take care of the instruction itself. So here you can take the substitutions. And later on, you try to harden everything, so it's not easy to be recovered. So you can apply upper predicates and harden them also with mixed Boolean arithmetics. And the reason is you want to end up like the guy on the right? You want to be successful. I mean, you want your malware to be fast and your revenue grow exponentially. And you don't want to end up like these guys on the left, where they missed the obfuscations. And yeah, unfortunately, it didn't pay out for them. So let's look at the technical view. Why do we want to preserve it? So here we see well-known pattern. This is what we call control flow flattening. And when we look at the graph, we can easily identify it, right? We have the entry block, we have the dispatcher in the middle, and then from the dispatcher, we see it's going to jump to all those basic blocks. It's flat, that's why it's called control flow flattening, and then it jumps back to the dispatcher until it finishes, right? So what happens if we directly apply the optimization and don't preserve the control flow graph? We end up with this here. And this is the function that I showed in the beginning. It should just fold into one line, but it doesn't, right? I mean, and we didn't gain anything. It looks even worse than before. Now we have to pass the blocks. We need to find all this information. So life will be difficult. And this is basically the reason why we don't want to preserve it in the beginning. We want to weaken the security at the beginning and then start the process. Yeah. So next thing is, so we took care about the CFG. Let's start to weaken the arithmetic expressions. So here we have tools like Zimmer++ or Super that will help us. So the tools will basically try to find those expressions, simplify them with one of the algorithms, and then reason about the outcome. Yeah?
OK, so just a quick review about what MBAs are, or mixed Boolean arithmetic expressions are. So if you take the traditional arithmetic operations like plus, minus, multiplication, and combine them with the Boolean operators we have, XOR and OR, you get this mess. Like I have an example over here. Now, it's a mess because when you try to solve them, there are no rules. So if you recall those distributivity and associativity principles, so they are not available over here with these expressions. There is no interaction. And this kind of, when we use them, this kind of makes the whole program obfuscated, or the expressions obfuscated, like how to resolve them, how to solve them. You can use SMT solvers, but beyond a certain complexity, they don't work. They might become too slow, or they may not solve altogether. So we have in recent times, got some tools which specialize in breaking them, Simba and Gamba. Simba++ is like an improvised reincarnation of these tools. Peter?
Yes, so Simba++, this is a tool I wrote. You can find it in my GitHub repo. So basically, it tries to solve the problems to find those MBAs. And the small functions is quite easy to identify them. But imagine like a big function. So where are the expressions that you're looking for? Where do they start? Where do they end? Yeah, we need to somehow solve this problem. And Simba++ tries to parse the LLVM IR, identify those expressions, go through the AST and try different combinations, apply the Simba algorithm, or Gamba. You can also choose Gamba. And then it's going to, when it finds a simplification, it's going to replace the expression with the simplification.
Example. So we have one example on the left that it's a LLVM IR representation of one of the MBAs. And once we simplify it, it's a pretty simple expression right at the bottom. The important thing to note is that, like in the original expression, there were 9 operators. But once you simplify it, we are left with only 2 operators. And then on the right-hand side, you can see that there were 13 operators in this MBA, but once you resolve it, it's just a constant. So there are no operators, just one constant is there. So if we can do such things in the real code, then after that, the LLVM will take care of the other things.
Mm-hmm. Yeah, so there is one way to solve this, but in our case, maybe we don't care about the constants, right? Maybe we try to target the basic block directly. So when we slice the expression, slicing means basically we just isolate the expression itself. There are different ways to do this. Either you walk by the users or the users of the return value, or you can use optimization to do it for you. But in this case, we directly slice the expression, so you can see the sliced LLVM IR. Then we're going to target the select directly. Right? We can translate the we can translate the expression into an SMT formula. So SimLLVM does it for you. It's also available in Squanchy. And then we can try to solve for possible values. So what we can do is we can ask if this Z3 expression minus symbolic value V is always equal 0. So the first result we get is SAT. Yes, there is a solution. And we get the constant 1926. So this is one possible solution, right? Now we can ask, oh, is this expression minus V equals 0, and are there any other solutions than 1926? Oh, we get unsat. Perfect, so there's only one solution. So we prove that this expression will always fold into sum plus 1911, yeah, so, and plus the constant 15 at the end. But yeah, so we proved it that it's equal, okay? So next step, we weaken the control flow graph, we weaken the instructions. So let's try to extract the functions and make it readable for us humans. So we're starting the brightening step. So first what we do is we replace the instance in the beginning that we allocated back to its original argument. It's still there, so we can just replace all users. This is just in case you have any calls, and those calls might use this parameter. We don't want to use it the internal allocer, so we just replace it back. Then we're going to clean the leftover initialization code because we don't need it anymore. It should be not used anymore, just in case. So we're going to clean this one out. Yeah, so, and once we're done, we're going to extract the de-obfuscated function and data segments because it might still rely on some data. So we put them into its own module. It's based on LLVM extract, a very powerful tool. And You can further then process it with still Simba++, Super, or any other tool that you have available. And one last step that we also apply, it's the LLVM module optimization. So far we were using function optimization, but what we notice is that the module passes sometimes behave more powerful. We don't know exactly why. This is some internal reason, I guess, but this is what's happening. So it's a good idea to just run the module passes once again at the end. So now we can do recompilation. We have the LLVM IR, so we can either stay with LLVM IR, or we use the ARM64 backend to generate ARM64 code for us. As I mentioned before, you can compile it to an object, load it in IDA, Ghidra, and use the decompiler.
OK, so now we have a very good understanding what's really going on, what we are doing. Let's apply to the real world. So we'll try applying all this knowledge we gain on the real world examples. So just a reminder, so this was the original input we took. We need to focus on the 4 expression and just look at the size of them. So now this is LLVM, OLLVM. We apply OLLVM instruction substitution obfuscation, and we try to solve using the LLVM optimization, no other tool. On the left is the obfuscated one. On the right, you can see all the expressions are, we recover them in the original form. We make examples difficult now. So we run the substitution pass 3 times. And on the left, I have only the second expression, which is like quite big now. And on the right, we have the simplified one. And if you look at the second expression, the box is quite small. Like we are simplifying it. And for the 4th expression, we recover the original one. So this is the case where LLVM either is breaking it completely, or at least it's weakening it, so which is pretty good result for us. So we have LLVM optimization working for us at least. But there are shortcomings to this, as we just saw. So some of the shortcomings are like whenever we apply any obfuscation related to the flow, for example, control flow flattening or bogus control flow, LLVM optimizations are hit and miss. Like if it gets too complex, you may not be able to recover it. Similarly, for the MBAs, like yeah, if you have complex MBAs, LLVM won't be able to solve it. And there could be other cases as well when you start applying in the real world situation. Yep, some thinking time. And then we just talked about like using Simba, Gamba, and these tools. So let's use them. So continuing with the example, we applied Simba plus, like first Simba. And you see that we recovered the second expression now. And the other 2 expressions are further simplified. And if we apply Gamba now, it reduces further. So we are moving in the right direction just by using these tools. So how about we make it or take a bigger complex example now? So now we take the case with Polaris, the other obfuscator. We apply instruction substitution 3 times, like a create big complex program. And we apply what we just said, like Simba, Gamba, and LLVM optimization, and we recover everything. So this is going good. So yeah, we have Simba++ in our pipeline now. Now, Peter just mentioned about Super, so just a quick introduction about Super. So Super is a synthesis-based superoptimizer. The original idea was to find new optimization passes for the compilers. So compilers may not be using all the optimizations which are available, or they may not implement it. So the idea was Super was to figure out these new optimization. But good thing for us is that it works extremely well for de-obfuscation. Now, there are 2 passes or 2 features that we use. So one was CGIS algorithm, which is a synthesis-based algorithm. And the other one is data flow pruning algorithm. Now, the second one is really important because it kind of solves a problem when we are trying to deal with the obfuscated control flow, like the bogus control flow or flattening one. And we just applied them. So now here is the case where we have a bogus control flow using Hikari applied twice. Just to show you that opaque predicates are introduced, the graph is complex. And we apply Super, now we recover everything. So no extra code written, just using Super, right features. Yeah, we recover everything. Yeah, this was our final thing, like Super is the real thing. OK, so we have Super now. Let's make it more complex. Like we are going in the right direction. So just to indicate, on the left-hand side, it's like a long, complex, obfuscated code, which is using substitution, bogus control flow, splitting of the basic blocks. And we applied all the tools that we have, LLVM, Simba, and Super. You see that 3 expressions are recovered. The last one is weakened, the 3rd expression. But it's manageable. Like we are in good direction. So after all this testing, we are like, OK, let's try to get some real-world examples. What's happening in the real world now? So we see that WebAssembly is being used a lot to write crypto miners as malwares. So you go to some website, these things will be loaded, will be doing crypto mining on your browser. And then we came across this paper where they say that if you take a malware, you apply Wasm-mutate, the tool we just mentioned earlier in the talk, it kind of creates polymorphic malware. So there will be some obfuscation, and yeah, the new output will behave like a new malware. No virus engines or antivirus engines are able to detect them. That's what they demonstrated. So what's Wasm-mutate? Wasm-mutate is a tool which kind of applies 3 kinds of transformation, like peephole optimization, so there are some hard-coded rules. It can add new function, can delete new function, so some changes through the structure of the program, and then it can change some control flow. For example, you can unroll the loop. So it do some kind of a pseudo-obfuscation, we can say.
OK.
More time.
Small demo.
Yeah, I get them.
Take this one. So we apply Wasm-mutate on a function. We go crazy 3,000 times. I think we hit the limit almost of WebAssembly. So let's run our showcase, run Debo. Yeah. Let me move the idle screen here. This is the function that we targeted. This is the one that you saw. OK.
Takes
Really
time to load.
Let's do the whole view. So basically, we created this huge monster, right? So let's see if Squanchy is successful. Maybe just one thing. So we started with 806 bytes before the mutation. We ended up with 100 kilobytes. So Squanchy started with 200,000 instructions. After the first customization pipeline, it was folded into 20 instructions. We still continue our de-obfuscation pipeline. And after we recompiled into the object, yeah, we end up with this here. So it's successful. So we proved that the Wasm-mutate is basically not resistant to compiler optimization. Here. OK.
Yep. OK, just a summary from the demo. Now, yeah, you take this one. Yes.
Yeah, kryptonite. Yeah, so also we tried to apply it on some malware samples that we found in the wild. There are not much, and people don't share them, at least if you're not working for the right company, I guess. So here we found at least one from a paper in a repo on GitHub. So they were comparing their kryptonite unobfuscated to an obfuscated version that they found. And we tried to de-obfuscate one of the functions to see how our tool behaves or how our pipeline behaves, and we could completely recover it. At the beginning, we thought, OK, something went wrong because there was additional code. But after some time, we discovered that the obfuscation tool inlined some code into this function. So this was basically real code that belongs to it, but was different from the original source code. But it was OK, so we could fully recover this.
OK, so yeah, we have some great results, but it's not over. Like, we can still improvise on things. For example, can we compile it to a replaceable equivalent de-obfuscated Wasm binary? So you just take the de-obfuscated one, replace in the original place. That's something we need to just get few things working. Like, we are almost there. We want to improve the de-obfuscation times a bit with Squanchy and iterative control for graph recovery.
Yeah, maybe to explain why. As I mentioned in the beginning, we cover the whole control flow graph at once. So and we also increase the thresholds of the LLVM optimizations, right? So they don't block anything. And this might take too long. So if you're going to de-obfuscate a function, it might never end. And this is not what we want, right? But when we worked on Saturn, we did a different approach. We iteratively we covered basic block by basic block. And we would like to take this concept back into Squanchy and iteratively basically lift those basic blocks, simplify them, and this should help basically to lower the execution time of Squanchy.
Before conclusion, you want to show the other demo?
1 minute, no.
OK, all right. OK, so we conclude then. So in terms of tooling, we would say that we can use the existing tooling for WebAssembly. We don't need to look into the new tools. So there's a lot of work going on, especially in academia. We see research papers like there are tools like Wasm-mutate coming up for for obfuscation, Wasm for symbolic execution. But what we see now, if we have LLVM IR, we can just use the existing technology. We showed that we can obfuscate, again, using the existing technology. We talked about Squanchy, that how do we lift from Wasm to LLVM IR. And it kind of, make the things good for the LLVM optimization. We can apply them. They work out of the box then. We talked about de-obfuscation, the various tools we can use. Again, that's a great thing about having LLVM IR. So all the research which is done related to LLVM can be applicable now. So for example, you want to use CLI code. You want to write your own passes? Yeah, go ahead. You can write one now. And then we can do malware normalization as well. So as we show, you can have like simplified malwares. The last one is the interesting one. So yesterday we were in the speakers lounge and we were talking to Angelo, who presented yesterday. And he mentioned about, he has some Wasm obfuscated binaries. And we were like, yeah, can you give it to us? We want to give it a try. And on the left-hand side, you see it's like one of the obfuscated functions from that binary, which is using dispatcher-based control flow flattening. And on the right-hand side, you see the de-obfuscated one. And actually, when you just look at the decompiled code of this one, it's very much readable. You know what the logic is going on. So we kind of applied in the real world during the conference itself. Yeah, that's it. So
thank you, everyone.
Please? Thank you.
All right, we do have a little bit of time for questions, unless there is, and people want to go, if there's no questions, we can go back and do the demo. We do have a little bit for either questions or demo if you want to do it, but, or we can let people go to lunch early, which is never a problem too. So any questions? Ron, yep.
You said during the presentation that there is not a general solution to the MBAs. Is that like a provable statement, or is that just because nobody's come up with a general solution to solve?
You mean there is no solution for MBAs? No.
Oh. Is there no generic solution mathematically?
Oh, yeah.
There can ever be, or we
is,
just don't have good solutions right now?
Yes, we have solutions thanks to one company called Denuvo. So Simba is the best algorithm we have right now. I think there are also others. Tim, that does the training, he also implements some of them.
There's not like a proof that says this is not possible.
Yeah, exactly. There is no proof. And we see there is a good algorithm. Simba is pretty good at doing this. Yeah.
Anybody else? Thank you.
So what was your conclusion for your customers?
We go ahead with it.
Yeah, we can go ahead. I mean, we have our internal obfuscation tool. Of course, we didn't present this one and the results. But when we applied the attack, we understood what we need to do to make it harder for those kind of tools. And this was the goal for us, right? We need to implement some new passes because we see the stack variables are easily accessible because the stack-based machine, you get them for free, more or less. You see the memories. We have the CLOCKers. I didn't talk about that. But alias analysis is working fine. So we get some ideas what we might need to do in the future. And once we do this, yeah, we might move to WebAssembly.
Great question. All right. Let's go ahead and enjoy lunch. One more round of applause. Thank you.
Thank you.
Thank you, everyone.
Good, man.
Good, man. Yeah.